Okay, welcome to this video designed for people who couldn't attend this week or last week in the first couple of weeks where Year 10s were called into FCC tutor group by tutor group. So the purpose of this video is to really go over the key points of electricity. And please stick with electricity. If you don't get it the first time, you're not on your own. It's not easy. Everybody who properly understands it at GCSE certainly has probably had to persevere and didn't get everything first time. So don't worry at this stage if things aren't clear and you can't remember too much. We're going to do our best to kind of link together some of the important keywords and concepts so we can build a realistic model of electricity that you're expected to know. And then use some rules to help you work out things in circuits given knowledge of other values which you'll be given. So let's make a start. So first thing I'd like you to do is pause this video and take a piece of paper and note down what you understand by the words in the blue box. So you probably don't understand some of them. You probably might think that some of the things you've got in your head are wrong, but write down what's in your head at the moment about these things. And I challenge you, try to get about between 3 and 5 things written down. You might have heard of an electron or a coulomb of charge. You might have heard about current and voltage. You might know which words to link with positive and negative. You might know what amps measure or volts measure. You might know how voltmeters or ammeters are connected up and what the circuit symbols are. You might know what resistance is and how it affects current. You might be able to link the concepts of a cell or a battery. So press pause and note down what you can. So let's make a start. So here I want to do a job. I want to make my bulb light up. So my bulb is in this picture here, and I'm going to take a battery. So batteries, when you buy them from the supermarket or elsewhere, they look like the battery at the top there. If you actually unpeel the metal sheath around the outside, you can see that batteries are just several cells connected up. So if you can see where my mouse pointer is pointing, if you connect up several cells in series, then you get a battery. Now, to get your bulb to light up, you have to add in connecting wires. So I'm going to hopefully be able to make my connecting wires appear there. And now we've got a series circuit. A series circuit is when there's one route around the circuit, here one closed loop, and the energy that's stored in the chemical store of the battery will somehow be transported to the bulb and light it up. And there must be something in the wire that's transferring this energy. All right. So for ages we didn't know as scientists what this was. So that was about 200 years ago when we kind of were able to do things with electricity and to see things happening, but we didn't really know on the level of particles what was transporting the energy. To save us drawing pictures and sketches, because science isn't art, we use circuit symbols. So this is the circuit symbol for a particular battery made of the individual circuit symbols for cells connected together. Remember, the taller, thinner terminal is positive and the shorter one is negative, and this is the circuit symbol for a bulb. Okay, so something to bear in mind is that in a solid, particles are all touching and all vibrating back and forth around a fixed position. But what makes metals unique is that they have a charged particle which isn't attached to these particles, which are able to move in amongst them. And so 200 years ago, we knew that this charged particle must exist, but we didn't know what charge it was, and we didn't know how much charge it had. And we weren't in a position to see, using microscopes, inside a metal on such a small scale. We just didn't have the capability in terms of technology then. So what we did is we created a model, and we said, look, we don't know what it is, but let's say that the charge thing that's moving in a metal wire is called a coulomb of charge. And by definition, each coulomb is a positive unit of charge. So it's really important to remember that charge, these little particles, which we're modelling as coulombs at the moment, exist in the metal, and they don't come out of, they're not created from the battery or cell. They're in the metal in a position to be given energy and in a position to be got moving by the cell or battery. So in this diagram here, we've got the positive terminal on the left, the negative on the right, and the positive coulombs are being repelled by the positive terminal and attracted to the negative terminal. And the more positive the positive terminal is, or the more negative the negative terminal is, the more motion you're going to get. And we'll break that down in a more scientific way with useful strict definitions as we go through. So we didn't know that coulombs existed, but we made a model which allowed us to go on and try to explain and understand certain things. So around the turn of the 19th into the 20th century, so we're talking about 120 years ago, we actually discovered that these little particles doing the moving weren't coulombs of charge. They weren't positive charges at all, but they were much smaller negative particles called electrons, and they moved the other way. They moved from negative to positive. And so this often freaks kids out. They're like, well, God, sir, this is hard anyway. I don't like electricity. So do you want me to think in terms of coulombs, or do you want me to think in terms of electrons? Well, what my advice is learn this Coulomb model first. This is what current and voltage are defined using. And just remember that actually electrons are the thing moving in the opposite direction. But you don't have to ever kind of break down questions at GCSE using the electron model. We're talking about the Coulomb model. So we can talk about coulombs of charge moving and coulombs of charge carrying energy. So coulombs are the main thing to process questions with, and then to work out voltages and currents. But just bear in mind that electrons are the actual particles, because if you go on and study science further, that becomes more and more important. So I've got my series circuit here again, one battery, 2 volts, made up of 2 cells, so each cell must be 1 volt. And coulombs, because they're positive particles, they come out of the positive terminal, go around, make the bulb light up, and then go back round to get more energy. So what is really important is I've drawn a wire here. So this straight line and this straight line represents the edges of the wire, and I've drawn my positive black circles which each represent coulombs, and they're moving from the positive terminal to the negative terminal. And if I have a 2 volt battery, what that means is each coulomb of charge is given 2 joules of energy. So 2 volt battery would give each coulomb 2 joules, and that 2 joules from each one would go into the bulb and then come out as light energy, and maybe a bit of heat as well. If you touch a bulb, you realise that the temperature rises. So let's change it now. So let's change it and say, well, I haven't got a 2 volt battery, I've got a 5 volt battery. So this would mean what's actually happening is that the chemical energy is 5 joules is being given to each coulomb of charge to then take to the bulb as before. So, the bulb is going to be brighter because each coulomb is now carrying 5 joules of energy rather than just the 2 before. And I've represented that with larger red circles there. So key points to pause and note down. Voltage is the amount of joules of energy given to each coulomb of charge, and that voltage is directly related to energy. So we can measure voltages, and when you're measuring energy leaving the circuit, so if we place our voltmeter correctly wired in parallel, so with two connections across the bulb whose potential difference we're measuring, voltage, when you're measuring voltmeters when connected correctly in parallel, will measure the amount of joules per coulomb of charge leaving the circuit in that position. So we're figuring out with this voltmeter here how many joules per coulomb are leaving the circuit through the bulb. So potential difference is just a different way of saying voltage when energy is leaving the circuit. So all energy is carried by coulombs from the cell or battery. Then it must leave the circuit at some point. We have 2 joules of energy coming into the circuit per coulomb. So just add that in. So the potential difference, I'm just correcting typos as I go, across the bulb must also be 2 volts, because this is the only place that energy can leave the circuit. So yeah, if the battery is putting 2 volts into the circuit, 2 joules per coulomb, then 2 joules per coulomb must be leaving the circuit. So the potential difference across this bulb must be 2 volts. So this is a kind of situation where we use the conservation of energy. So energy cannot be created or destroyed. It can only be transferred into other stores. So we've got 2 volts coming in, so we must at some point have a total of 2 volts coming out, and we've got that. So on to current then. So you measure current using an ammeter, and ammeters are not placed in parallel, so they're not wired up across components, but they're placed in series. That means in the circuit itself. So current is measured by ammeters in the key points in amps, and ammeter are placed in series, so in the circuit themselves. Now, the eagle-eyed people amongst you would have noticed that before, when we moved from a 2 volt battery, not only did the energy change, but also the size of my arrows changed, because the second job of a battery or cell or any power source in a circuit, whatever it may be, is to get the coulombs moving. So the bigger the voltage, the more movement of coulombs you're going to get. And we need to be strict about quantifying, so putting a number to we need to be strict about quantifying the flow of coulombs. All right, because flow is a pretty general word, and lots of times students get this a bit too loose and they end up losing marks. So strictly speaking, current is the number of coulombs past a point in a second. So when we had 2 volts, we had a much smaller arrow, so we'd have a much smaller current than if we had 5 volts. We have a much bigger arrow with 5 volts. It's like voltage, sometimes people like to consider it as a push. So 5 volts is a bigger push than 2 volts, so we'd get more coulombs moving. So a scientist would say, oh yeah, we'd have a higher current because more coulombs would pass a point in a second. So this bit here is really key to note down. In fact, all of these key points are key to note down, but this third bit I've put in bold because it's essential. So pause the video and make a note of those key points. So now we know that cells or batteries or power sources do 2 things. They give coulombs of energy, coulombs of charge energy to take around in the circuit, and they get the coulombs moving. They get current flowing, and the bigger the voltage, the bigger the current that flows. So we have a series circuit here. We only have one closed loop. So the first circuit rule, the easiest one, is about current in a series circuit, and it's dead easy. If I've got an ammeter here with 2 amps on it, and I've got an ammeter here that I don't know the reading of, well, the rule to remember is the current anywhere in a series circuit is the same. So that one also must be 2 amps. So please, can you write down that rule? The current anywhere in a series circuit is the same. So I'll just underline it. There you go. So here we go with how developing a rule for voltage in a series circuit. So there's a rule which helps you figure out voltages. Now here we've got a battery putting 2 volts into the circuit. So the first thing to realise is that we must in total have 2 volts coming out of the circuit at whatever point. So we've got 2 points which we're considering. Across the first bulb being measured by V1, that voltmeter, and across the second bulb also being measured by the voltmeter V2. So if the bulb, so really key points, in series all potential difference splits according to resistance. All components have resistance, even if they're not resistors. The higher the resistance of a component, the greater the potential difference across it. So in this case, I've told you in the question that we have identical bulbs. So that means that the resistance of the bulb with V1 across it is the same as the resistance of the bulb with V2 across it. So they have to have equal they have equal resistance, so they would have the same voltage across it. And we also know that when you add up their potential differences, you must get 2 volts, because the second rule down here, which I'd like you to write down remember, is the sum of the potential differences has to equal the sum of the voltages of the power source. We've only got 1 power source here, it's 2. So we know that V1 and V2 have to add up to 2. And also, they have to be the same number because they have equal resistances. So the only way you can meet those 2 criteria is if you have V1 and V2 both being 1 volt. So they have the same, they do indeed have the same potential difference, 1 volt, and if you add them up, they do make your 2 volt input voltage. So pause the video, copy down these circuits and see if you can work out the unknown values with a question mark. So let's go over the answers. So in question number 1, the bulbs have equal resistance again. So V1 and V2 have to be the same, and they have to add up to 10. So the only way you can meet that criteria if V1 and V2 are both 5 volts. So give yourself a tick if you said 5 volts for each one. The next one is a harder example. So this is your first example where the bulbs aren't of equal resistance. So bulb A has a resistance of 10 ohms. So bulb B has a resistance of 40 ohms. So 1/5 of the total resistance, which is 10 add 40, which is 50, is across bulb A's resistance. So what is 1/5 of 10? Well, 1/5 of 10 is 2. So V1 must be 2 volts. And there's 2 ways to now figure out what the voltage V2 is. So if 1/5 of the resistance is across the first bulb A, then 4/5 must be across the other one, which is it's 4 times as much. So what's 4 times as much voltage as 2? Well, 2 times 4 is 8. So that's 8 volts. and you can check you're right, because the sum of our output voltages should equal our input voltage in this case. So has it worked? So 2 add 8 is indeed 10. So we've been able to check our answers ourselves. So this is your first example where the resistances in series are not the same. Okay, on to parallel circuits. So this is a parallel circuit. We have a branch where we have, a closed loop where my mouse has just gone around here. That's one closed loop, and that's being measured by V1. And V1 isn't a part of the circuit itself. We don't count voltmeters as part of the circuit. So the second closed loop is where my mouse pointer is going around now. And so we have more than one closed loop, so we have a parallel circuit. And V2 is measuring the potential difference across this bulb on our second closed loop. So it's really easy, the rule here. So the voltage across each branch in a parallel circuit is the same. So if you've got 10 volts across this first branch with the battery in, you must also have 10 volts across this branch. And you must also have 10 volts across this branch. So please pause the video and write that down. So in a parallel circuit, the voltage across each branch is always the same. So moving on to the last bit then. So current in parallel circuits. So in this case, we've got 4 ammeters in our parallel circuit. And our coulombs come out of the positive terminal, and we've got 4 amps coming out on ammeter A1. So we have our 4 amps will continue around the circuit and get to junction A. And current can do 2 things at junctions. It splits where a smaller number of input pathways goes to a bigger number of output pathways, like this. So I've got 1 coming in, I've got 2 coming out. And at B, you've got 2 pathways in and 1 out, back to the negative terminal. So at junction B, the current would recombine. And so how will our 4 amps split at junction A? Well, current splits according to resistance. And the bigger the resistance of our bulbs in this case, so the bigger the resistance of each bulb will mean a smaller current goes through each branch. So in this case, I'm going to say that each bulb has an equal resistance. So bulbs have equal resistance. So what does that mean in terms of the split at A then? So it means if they split equally, well, the only way you can split 4 equally is 2 on the middle branch and 2 on the lower branch, so 2 amps on each. So 2 amps would go across the middle branch to B, and 2 amps would go along the lower branch to B. What will happen? Well, the current will recombine. So what's 2 add 2? Well, that's 4 amps. And you know when you've got this right, because the current out of the positive terminal will be the same as the current going into the negative terminal. So I've got 4 amps coming out of the positive terminal and 4 amps going into the negative terminal. So that's right. So please stop or pause the video and note down these key points.